Hello. Welcome to Sleepy Discoveries, a journey to sleep through calm discoveries. Tonight we drift into the quiet world of winter, a season that reshapes the planet in ways most of us never notice. As the air cools and the light withdraws, familiar landscapes begin to feel distant, almost unreal. Winter is not simply cold weather, it is a transformation written into the physics of nature and the rhythms of life itself. In winter, silence is not empty, it carries meaning. Hidden processes rise closer to the surface, and as the world slows down, its deeper workings become easier to sense. Beneath frozen ground, within still air, the planet remains quietly active. If you enjoy these gentle journeys, liking or subscribing helps others find their way here too, one sleepy soul at a time. For now, just breathe. Let your eyes grow heavy, allow your body to soften, and let the calm of winter guide you towards sleep. Let us begin. Some snowfall carries traces from far beyond Earth. As snowflakes grow in the atmosphere, they collect more than water alone. High above the ground, microscopic grains of cosmic dust drift slowly downward. Many of these particles began as fragments of comet tails, asteroid collisions, or tiny meteoroids that burned up high in the sky. When conditions are right, forming ice crystals sweep up these particles, sealing them within layers of frozen water before settling on the surface. Later, when snow from remote places is carefully melted and filtered in laboratories, researchers sometimes recover these foreign grains. Under a microscope, they may reveal exotic minerals, glassy beads formed by intense heat, or compositions that point to distant origins in the solar system. In this way, winter becomes a quiet courier, a delivery system for material that has crossed interplanetary distances. What appears to be a simple white blanket can hold a hidden record of events far beyond our world. Extreme cold creates sounds that do not exist in warmer seasons. On the coldest days, footsteps on dry, powdery snow can produce a sharp, squeaking crunch, a sound that vanishes as soon as temperatures rise. It comes from rigid snow crystals grinding and breaking under pressure, a behavior that requires both low temperatures and specific crystal structures. Lakes and rivers locked beneath ice can emit deep booms, cracks, and ringing tones. As temperatures shift, the frozen surface expands and contracts, sending vibrations rapidly through the ice and the water below. In quiet landscapes, these sounds can travel long distances, forming an eerie, distant chorus. Even thin ice over small puddles can produce bell-like tones when disturbed just right. In calm, freezing air, sound itself can travel farther, bending and reflecting through layered atmospheres, making distant noises seem sharper and closer than they truly are. Together, these effects create a soundscape that belongs entirely to winter, one that fades away when the world begins to warm. Winter can even cause rivers to briefly flow in reverse. Under certain conditions, the combined influence of ice, wind, and water levels can push currents against their usual direction. Ice jams form when broken ice accumulates in narrow sections of a river, acting like temporary dams and forcing water to back up. If upstream water continues to arrive, levels rise behind the blockage, and for a short time, surface flow near the jam may move upstream as the system seeks balance. Strong, sustained winds at wide river mouths can also pile water into bays and estuaries, raising water levels enough to support inland flow against gravity. When the wind eases, the ice breaks free, or water levels equalize, the river returns to its familiar course. but to an observer on the bank, it can appear as if the river has reconsidered its direction. On the coldest nights, the chemistry of the air we breathe can change. As temperatures fall and winds grow still, the lower atmosphere can separate into distinct layers. Cold, dense air settles near the ground, while warmer air rests quietly above it. This arrangement, known as a temperature inversion, acts like a lid over the landscape, trapping gases and particles close to the surface. Pollutants from vehicles, heating systems, and industry accumulate rather than disperse, and chemical reactions proceed differently in the dense, cold air. Some reactions slow as thermal energy drops, while others become more efficient as reactants are held close together. Nitrogen oxides, ozone, and fine particles can build to levels that alter both the composition and appearance of the air, sometimes creating the soft haze unique to winter. Natural emissions from soil and vegetation also behave differently, rising into an atmosphere that no longer mixes them away. As a result, the invisible mixture entering the lungs on a still, freezing night can be chemically distinct from the air that fills the same streets on a warm, breezy afternoon. Winter storms can generate electrical charges stronger than those in many summer storms. In certain intense systems that produce heavy snowfall, turbulence and collisions within the clouds create ideal conditions for electrical separation. Ice crystals, snow particles, and soft hail collide within powerful updrafts, transferring charge as they move. Over time, regions of positive and negative charge separate within the cloud, building an imbalance strong enough to discharge. The result can be lightning embedded within falling snow, briefly illuminating a storm that would otherwise remain dark and muted. This phenomenon, often called thundersnow, tends to occur near large lakes or coastal regions where relatively warm water fuels strong convection in cold air. Because snow scatters light differently than rain, these flashes can appear softer and more diffuse, sometimes little more than a trembling glow within thick snowfall. Freezing temperatures also change how light moves across the landscape. Fresh snow reflects most of the sunlight that reaches it, turning open ground into a surface nearly as bright as desert sand. This high reflectivity alters the balance between incoming and outgoing energy, cooling the air just above the surface and shaping how atmospheric layers form. At the same time, strong temperature gradients near the frozen ground can bend light as it travels, subtly shifting the apparent position of distant objects. Under the right conditions, this bending can stretch horizons and elongate structures, making the world appear slightly unfamiliar. Winter does not silence the planet. It invites us to listen more closely, so stay here in the quiet. Let your breathing slow, and allow the cold, gentle stillness of winter to carry you into sleep. Under the right conditions, distant features can seem to shimmer or drift as if suspended in the air. Ice crystals hanging in the atmosphere behave like countless tiny prisms and mirrors, bending sunlight into halos, pillars, and soft veils of brightness that hover above snow-covered ground. Even artificial light changes character in winter. City lights spread farther when reflected by fresh snow and low clouds, illuminating the night sky in ways that look strikingly different from summer darkness. Together, altered reflection, scattering, and refraction turn winter into a season where the familiar rules of light quietly shift. Winter has a way of revealing hidden physics, processes that remain invisible during milder months. When temperatures fall far below what we consider normal, matter enters regimes rarely encountered in daily life. Liquids thicken and creep instead of flowing freely. Gases lose energy until molecular motion slows to a near standstill, allowing subtle forces, usually overwhelmed by heat, to become significant. At sufficiently low temperatures, some metals allow electric current to pass through them with almost no resistance, turning ordinary wires into nearly perfect pathways for electrons. Magnetic behavior can change as well, as materials transition between different states when thermal motion weakens. Even water reveals unexpected complexity, forming multiple types of ice with distinct crystal structures and mechanical strengths. For scientists, winter acts as a free outdoor laboratory, offering extended periods of natural cold that would otherwise require complex equipment. For everyone else, it serves as a quiet reminder that the properties of matter are not fixed. They depend deeply on their environment. In some places, snow can form without a single cloud in the sky. On the coldest, clearest days, the air near the ground may fill with tiny ice crystals that sparkle in sunlight, even as the sky remains an uninterrupted blue. This phenomenon is often called diamond dust. It occurs because extremely cold, still air can hold trace amounts of water vapor. Instead of rising to form clouds, water molecules freeze directly around microscopic particles or form ice spontaneously. Each crystal is small, often a simple plate or needle, and falls so slowly that the air appears filled with a glittering mist. At night, streetlights transform these drifting crystals into glowing columns and halos, making familiar streets feel strangely otherworldly. Aircraft, chimneys, or human movement can disturb these delicate fields, carving invisible paths through the shimmering air. It is a form of precipitation that blurs the line between weather and atmospheric optics. Winter also reshapes the color of the sky in ways no other season can. When the sun travels low above a cold horizon, its light must pass through a thicker layer of atmosphere before reaching the eye. Along the way, it encounters more air molecules, more suspended particles, and more ice crystals lingering at higher altitudes. Shorter wavelengths, blues and violets, scatter more efficiently, leaving behind the warm reds and pinks that dominate winter sunrises and sunsets. At the same time, cold air holds less moisture, often producing clearer conditions and reducing the hazy veil that dulls summer colors. The result is twilight that appears sharper and more saturated, deep cobalt overhead, with vivid bands of orange, crimson, and purple near the horizon. In polar regions, where the sun barely rises or sets for long periods, this effect can stretch into hours-long glows, resembling endless dawns or dusks. High-altitude ice crystals then bend and reflect this colored light into arcs, pillars, and subtle glimmers, rarely seen during warmer months. Freezing air can make ordinary materials behave like entirely different substances. Rubber that bends easily in summer stiffens and becomes brittle in deep cold, snapping sharply instead of stretching. Plastics that feel tough and resilient can suddenly fracture under loads they normally withstand. Metal contracts as temperatures drop, altering how moving parts fit together, tightening joints, shifting gaps, and changing mechanical tolerances in machines and buildings. Lubricating oils thicken, slowing gears and bearings that usually spin freely. Even glass can respond differently, becoming more vulnerable to thermal stress when one part warms while another remains cold. At the microscopic level, lower temperatures reduce thermal motion within solids. Atomic lattices become less forgiving when forced to move or deform, increasing the likelihood of cracking or failure. Engineers working in cold climates must account for all of these changes, selecting materials and designs that function across wide temperature ranges. For anyone paying attention, winter offers a visible lesson. Material properties are not absolute traits, but outcomes shaped by surrounding conditions. Snow can also fall beneath completely clear skies. This occurs when tiny ice crystals form in extremely cold, still air that never allows clouds to develop. Near the surface, the atmosphere may contain just enough moisture for crystals to assemble on microscopic particles and drift downward without turbulence. The result looks like a gentle, shimmering snowfall appearing out of empty air. Such events are most common in open plains, polar regions, and high-altitude landscapes where temperatures drop rapidly and the atmosphere remains exceptionally dry. At night, streetlights reveal the falling crystals as countless points floating in motionless air, creating the illusion of snowfall despite a cloudless sky. Because these particles are so small and light, they linger for long periods and usually settle without forming deep accumulations. They are also easily disturbed. Footsteps, passing vehicles, or even a faint breeze can scatter them instantly. This kind of snowfall shows that precipitation does not always require towering clouds. When conditions are calm, cold, and clean enough, ice can form quietly within the lowest layers of the atmosphere itself. Winter winds can lift particles far higher than summer winds ever could. As cold air masses sweep across large regions, they create strong pressure gradients that encourage upward motion in specific areas. Over open snowfields, wind can lift fine ice crystals from the surface and inject them into faster-moving layers above. These currents can then carry dust, salt, and tiny fragments of organic matter to altitudes far greater than those typically reached during warmer months. The structure of the winter atmosphere, with cold air near the ground and warmer layers above, can create sharp wind speed transitions that funnel particles upward. Once elevated, these materials may travel long distances, sometimes crossing entire regions before settling. Scientists study this process to understand how nutrients and minerals move between continents, as winter air can lift traces of soil, vegetation, and sea spray and carry them far beyond their points of origin. The combination of strong lifting forces and light, dry particles turns winter into a remarkably efficient transporter of material through the atmosphere. Cold season air can move dust, ice, salts, and organic fragments across great distances, quietly redistributing matter on a planetary scale. Living creatures respond to winter with transformations so profound that they can seem like entirely different beings. Cold seasons push biology into states that would appear impossible if they occurred in humans. Some mammals grow thicker, more insulating fur, but the changes go far beyond appearance. Certain species reprogram their metabolism to conserve energy, slowly and precisely burning stored fat to survive long periods with little food. Others reduce their heart rates to a fraction of normal levels, lowering oxygen demand so drastically that their tissues operate in an altered physiological mode. Some amphibians tolerate freezing itself. By controlling where ice forms inside their bodies and producing protective compounds that prevent cellular damage, they survive conditions that would otherwise be fatal. Birds also undergo internal changes. Some shrink or enlarge specific organs depending on whether they need to extract maximum energy from food or reduce weight for long migratory flights. These shifts are so extensive that animals behave like modified versions of themselves, optimized for cold rather than warmth. Winter forces biology to reveal its most flexible strategies, demonstrating how life can reorganize its inner workings when the environment demands it. Deep winter lakes can become vertically divided into layers that refuse to mix. As cold weather sets in, surface water cools until it approaches the temperature of maximum density and sinks. Above it, slightly lighter water settles into a stable arrangement that resists disturbance even when wind moves across the surface. When the lake finally freezes, the ice locks this structure in place. Light can still penetrate clear ice, allowing algae and microorganisms to remain active near the surface, while deeper layers fall into near darkness. Nutrients released from bottom sediments accumulate slowly, undisturbed by circulation. At the same time, oxygen from the surface struggles to reach deeper water, creating pockets with sharply different chemical conditions, only short distances apart. These layered systems behave like miniature oceans, complete with their own internal structure, circulation limits, and seasonal rhythms. When spring arrives and the ice melts, the entire water column finally mixes, releasing nutrients, carbon dioxide, and other trapped substances back into the upper layers. The legacy of winter stratification continues to shape the lake's biology long after the ice is gone. Frozen ground can exert enough upward force to move heavy structures. This process begins when moisture within the soil migrates toward advancing freezing fronts. As water turns to ice, it expands, forming lenses and pockets that push the surrounding ground upward. The continued draw of water feeds this growth, allowing the ice structures to enlarge over time. Gradually, the surface can rise by several centimeters, exerting significant pressure. Buildings, roads, and fences may tilt, shift, or crack in response. This movement is most common in regions with repeated freeze-thaw cycles, where surface soils hover near the freezing point. Different soils react in different ways. Clays and silts, which retain more water, undergo larger volume changes. Sandy soils are less prone, but under the right conditions, they too can heave. Engineers account for these forces by extended foundations below, expected frost depths, or using materials designed to tolerate movement. For anyone observing the winter ground closely, frost heave is a reminder that the surface beneath our feet is not static. It is a dynamic layer that responds dramatically to temperature, moisture, and structure. Winter may appear to pause the ecosystem above ground, but below the surface, life continues. Plants stop growing, insects vanish from sight, and many animals retreat into shelter. Yet beneath the snow, the soil remains surprisingly active. A thick snowpack acts as insulation, trapping heat from the ground and preventing extreme temperature swings. This creates a protected zone where microorganisms continue breaking down organic matter, releasing nutrients that plants will rely on in spring. Small burrowing mammals carve tunnel networks beneath the snow, feeding on seeds, roots, and each other, an unseen world hidden from above. Fungi continued decomposing leaf litter and fallen wood, slowly recycling material that sustains the forest floor. In frozen streams, aquatic insects remain active beneath the ice, feeding and growing until warmer water returns. Even plant roots maintain subtle chemical exchanges with soil microbes. The visible landscape may seem still, but beneath it, a quiet engine of life continues to turn. Winter divides the ecosystem into layers, one appearing frozen in time, the other preserving the momentum needed for the next season. Snow crystals themselves reveal extraordinary sensitivity to microscopic changes in temperature and humidity. Their shapes, plates, needles, hollow columns, dendrites, and intricate branching forms emerge from subtle shifts in atmospheric conditions as they grow. Slightly warmer air favors broad, flat crystals. Colder conditions encourage long, slender forms. Tiny variations in moisture influence how quickly different surfaces grow, shaping each crystal's symmetry and complexity. Because the atmosphere is never perfectly uniform, a single snowfall can contain countless variations. Scientists study these forms because each crystal preserves a record of the environment in which it formed. Even within a single snowflake, different sections may grow under slightly different conditions as the crystal passes through changing layers of air. The result is a collection of microscopic sculptures shaped by physics, each formed by a sequence of events that will never repeat exactly. Slowness becomes a natural design gallery, built molecule by molecule. Freezing fog can create ice coatings far thicker than the fog itself suggests. This occurs when supercooled water droplets remain suspended in stable air and freeze instantly upon contact with surfaces. As they collide with tree branches, power lines, or fences, they form thin layers of ice. As fog continues to flow, more droplets freeze and accumulate, producing deposits known as rime. Because this process can continue for hours, the resulting ice can grow surprisingly thick despite the minimal moisture involved. In winter, even the smallest particles, vapor, crystals, droplets, can quietly reshape the world. Accumulated ice often grows outward in the direction of the wind, forming delicate feather-like structures. These formations can evolve into intricate patterns that appear almost handcrafted. Although they are shaped entirely by atmospheric conditions, they differ greatly from the clear, solid ice created by freezing rain. Rime ice is porous and airy, making it lighter in structure, yet still capable of weighing down branches, power lines, and exposed surfaces. In regions where winter fog is common, entire landscapes can transform overnight, becoming coated in pale, spiked growths that seem to emerge silently from the air itself. This phenomenon highlights how persistent microscopic droplets, once temperatures fall below freezing, can dramatically reshape the environment. Winter cold can also reveal thermal patterns across the planet that are otherwise difficult to detect. Under clear skies, when surface heat escapes rapidly, different materials release energy at different rates. Rock, soil, vegetation, and human-made structures each respond to the cold in their own way. The result is a subtle mosaic of temperature variations that becomes visible only when everything is exposed to the same intense chill. Scientists take advantage of these conditions to study heat retention, moisture levels, and material properties across wide areas. Cold surfaces stand out more sharply, allowing researchers to observe how landscapes absorb sunlight, how cities trap warmth, and how ecosystems manage energy under stress. Even wildlife movement can be detected as animals subtly alter the thermal signature of the ground. In this way, winter becomes a diagnostic season, revealing contrasts that remain hidden when temperatures are mild and uniform. The quiet clarity of extreme cold acts like a spotlight, illuminating the planet's hidden structure. Some insects survive winter by removing water from their bodies, avoiding death by freezing. This strategy, often referred to as freeze avoidance, works by reducing the amount of liquid that could turn into damaging ice. As temperatures drop, certain insects convert internal fluids into forms that draw water out of their cells. With less water present, ice crystals cannot form. Many also produce special compounds that lower their freezing point, allowing them to endure temperatures that would destroy most living tissue. Throughout deep winter, their bodies enter a state of near complete dormancy. Heart rates slow dramatically, metabolism drops to minimal levels, and movement ceases entirely. Yet life persists. When warmth returns, water flows back into the tissues, metabolism restarts, and the insect resumes activity as if the long freeze had been nothing more than a pause. This remarkable adaptation shows how far evolution can push life to survive conditions that seem fundamentally incompatible with biology. Snow cover can influence weather systems far beyond its immediate location. When a landscape is blanketed in bright, reflective snow, much of the incoming sunlight is sent back into space instead of being absorbed. This rapid surface cooling alters temperature and pressure patterns above it, creating dense pockets of cold air that behave differently from surrounding warmer regions. Storm systems respond to these contrasts, following corridors shaped by pressure differences. As snow-covered areas expand or shrink, these corridors shift, redirecting storms along new paths. In some cases, a large snowy region can act like a massive mirror, cooling the atmosphere above it and strengthening pressure systems that persist for days. This can reroute storms across entire continents, affecting where moisture falls, how intense weather fronts become, and which regions experience unusual conditions. Meteorologists closely monitor snow cover because its influence extends far beyond the areas where snow actually lies, shaping atmospheric behavior over vast distances. Winter nights also carry sound much farther than summer nights. Cold air changes how sound waves travel, especially when strong temperature differences exist between the ground and the air above it. On winter nights, the surface cools rapidly while the air just above remains slightly warmer. This arrangement causes sound waves to bend downward instead of dispersing upward into the atmosphere. As a result, distant sounds can reach listeners with surprising clarity, sometimes traveling several times farther than they would in warmer seasons. The stillness of winter enhances this effect. Snow-covered ground absorbs some noise, while reduced wind and surface activity leave less background sound. Human-made noises from trains, vehicles, or machinery may seem louder and closer, and natural sounds such as cracking ice or distant animals can travel astonishing distances. This seasonal shift reveals how changes in temperature reshape not only landscapes, but also the invisible structure of the air itself. Winter becomes a natural amplifier, giving the world a distinctly different acoustic character. Ice crystals suspended in the air can create halos, arcs, and pillars rarely seen during warmer months. When sunlight or moonlight passes through these crystals, the light is bent and reflected into precise geometric forms. In winter, especially under extremely cold and calm conditions, the atmosphere can fill with millions of tiny plate or column-shaped crystals. As they drift, they tend to align gently under gravity. When light enters one side of a crystal and exits another, it bends at specific angles, producing glowing rings around the sun or moon, sweeping arcs above streetlights, or tall columns of light that appear to rise from the ground. The exact shapes depend on the type of crystal and the angle of the light source. Winter provides ideal conditions for these displays, as cold air can support large numbers of crystals without melting them. The result is a sky transformed into a scene of optical geometry, turning familiar views into moments of quiet wonder. Frozen oceans can generate powerful sounds that travel across great distances. When sea ice forms over large areas, it behaves like a flexible sheet, responding to tides, currents, and temperature changes. As the ice expands or contracts, it can fracture suddenly, producing sharp cracks or deep, resonant booms that echo across the frozen surface. Some sounds originate beneath the ice, where trapped pockets of water shift or pressure redistributes along ridges where ice plates collide. Because sound moves efficiently through both ice and water, these vibrations can carry far beyond their source. In polar regions, explorers often describe long, drawn-out groans and rumbling tones that seem to come from nowhere. Each sound carries information about the ice's thickness, temperature, and internal stress. The frozen landscape is never truly silent. It is constantly communicating through slow movements and distant echoes, telling the story of a dynamic world locked in cold. A frozen ocean becomes a vast resonant body, quietly transmitting its constant internal adjustments. Winter temperatures redraw the boundary between land and atmosphere. As the ground cools deeply, the exchange of heat and moisture between the surface and the air is fundamentally altered. A layer of extremely cold, dense air settles close to the ground, forming a stable boundary that resists mixing with the warmer air above. This invisible barrier reshapes wind behavior, moisture transport, and the circulation of gases. In some regions, it traps pollution or humidity, leading to fog, haze, or frost. In others, it produces exceptionally clear air with remarkable visibility. Frozen ground also releases far less heat and moisture than it would in warmer seasons, removing a major source of energy from the lower atmosphere. Over time, a new equilibrium forms between land and sky. Winter, by changing the rules of heat and moisture exchange, effectively redraws Earth's interface with its atmosphere, influencing everything from storm development to regional climate patterns. Snow can insulate the ground so effectively that plant life survives even during intense cold. A blanket of snow traps heat stored in the soil and prevents rapid temperature swings. Even when the air above plunges far below freezing, the soil beneath deep snow can remain near the freezing point, creating a stable environment where roots, fungi, and microbes continue limited activity. This insulation protects plant tissues that would otherwise be damaged by extreme cold. In forests and grasslands, snow becomes a protective layer that allows seeds, dormant buds, and root systems to endure conditions that exposed air could not. Between the soil and the snow exists a narrow, hidden world where temperatures remain relatively constant and small organisms can move safely. The survival of many ecosystems depends on this simple physical property. Without snow acting as a thermal shield, winter would destroy vast amounts of vegetation long before spring arrived. Snow is therefore more than surface cover. It becomes part of the biological infrastructure that preserves ecosystem continuity. Frozen surfaces can fracture into patterns that resemble a miniature version of Earth's continental crust. When a river freezes, shifting ice sheets respond continuously to current, temperature, and pressure. These sheets can break into sharply bounded plates that mirror tectonic structures on a smaller scale. As temperatures fluctuate, the ice expands and contracts, forming ridges where sections collide and channels where they pull apart. Over time, branching networks of cracks emerge, intersecting, reorganizing, and extending across the surface. Long, straight fissures may stretch for great distances, while finer fractures weave complex meshes nearby. Beneath the ice, flowing water adds further complexity by pushing upward at weak points or eroding support from below. The result is a dynamic system in which the frozen surface behaves like a cold analog of Earth's crust. Scientists studying the mechanics of solid materials examine these natural patterns to better understand how stress is distributed. For anyone standing along a riverbank, the frozen surface becomes a living map of tension and release. Winter sunlight can reflect off snow with an intensity rivaling desert sand. Fresh snow has a high albedo, meaning it reflects much of the sunlight that reaches it. Each snowflake scatters light in many directions, producing a brightness that can surprise even those accustomed to winter climates. This strong reflection further cools the surface, reinforcing a feedback loop that helps preserve snow cover. For humans, the glare can be powerful enough to cause discomfort or even snow blindness without eye protection. Animals in snowy environments adapt with specialized eyelids, pigmentation, or behaviors that reduce exposure. Snow's reflective power also reshapes how landscapes appear at a distance. Rocks, forests, and mountains gain contrast, and distant features become easier to distinguish. Despite the low angle of the winter sun, snow-covered terrain creates visually intense environments. What appears at first to be a simple white surface is actually a complex reflective system that redirects sunlight throughout the landscape. Cold air can sharpen long-distance visibility far beyond what is possible in summer. Lower temperatures reduce the amount of moisture the air can hold, producing dry, clear conditions when skies remain calm. With fewer water droplets and particles, light passes through the atmosphere with minimal scattering. Distant mountains, buildings, and landforms appear sharper and more defined than during warmer, hazier months. The stability of winter air further enhances this clarity. Without strong rising currents or turbulent mixing, the atmosphere becomes layered and still, creating a natural telescoping effect. In snow-covered regions, the reflective ground helps illuminate distant slopes and ridgelines, improving visibility even more. These conditions allow landmarks normally hidden to become visible across vast distances. Winter thus becomes an unexpected season of visual reach, offering clarity while sacrificing comfort, revealing far horizons that summer haze often conceals. Winter cold can slow biological processes to nearly a standstill. As temperatures fall, chemical reactions inside living organisms proceed more slowly, reducing energy demands and altering cellular function. Many species rely on this slowdown to survive harsh conditions. Some reptiles and amphibians enter states where movement nearly ceases and heartbeats weaken dramatically. Microorganisms reduce activity to conserve resources until warmth returns. Plants participate as well, shifting cellular mechanisms, lowering water content, and halting growth. This suspended state protects tissues from freezing damage and prevents metabolic stress. The slowdown extends across entire ecosystems. Predators hunt less, prey moves less, and energy flow through food webs declines. When spring arrives and temperatures rise, chemical reactions accelerate again, triggering a surge of activity. Winter acts as a natural reset across vast regions, demonstrating how deeply temperature governs the rhythm of life. Snow can also store precise records of weather over time. As it accumulates through winter, each storm leaves behind a distinct layer shaped by temperature, humidity, wind, and crystal structure. Over days and weeks, these layers compress, yet remain distinguishable through subtle differences in texture, density, grain size, and trapped air. Researchers dig snow pits and read these layers like pages in a seasonal archive. A light, fluffy layer may reveal calm snowfall, while a dense, rounded layer points to strong winds that pack the crystals together. In this way, snow preserves a quiet history of the atmosphere, recording the passage of winter, one layer at a time. Thin crusts can form when sunlight briefly warms a snowy surface before temperatures fall again. Dust or pollen settling onto snow may leave faint lines that later help identify the timing of specific weather events. Deeper down, layers slowly transform as snow compresses under its own weight. Yet many of the original patterns remain preserved, and each winter leaves behind its own signature. Storms, brief thaws, cold snaps, and atmospheric shifts all imprint subtle records within the snowpack. In regions where snow persists year after year, this layered structure becomes the foundation of glaciers. What begins as delicate snowfall gradually turns into a long-term environmental archive, frozen in place and quietly storing the history of past winters. Ice can also behave like a collection of miniature tectonic plates, colliding and grinding against one another. When rivers, lakes, or coastal seas freeze, the ice rarely forms a single uniform sheet. Instead, it breaks into separate sections that slide and rotate in response to currents, wind, and temperature changes. These pieces may drift together, colliding along edges that buckle upward into ridges or bend under pressure. In some cases, one slab overrides another, creating layered formations reminiscent of small subduction zones. Where ice pulls apart, long open cracks can expose the water below. Throughout the season, these movements continue, turning the frozen surface into a constantly shifting mosaic. Scientists studying ice mechanics observe these interactions to better understand how stress moves through solid materials. Indigenous communities and experienced winter travelers also learn to read these patterns, as the arrangement of ice plates can reveal safe crossings or hidden dangers. The changing surface is a reminder that frozen water is not static, but a responsive system shaped by forces above and below. Winter clouds often contain more ice than liquid water. In cold season conditions, temperatures drop low enough for tiny droplets to freeze into crystals. Even droplets that remain liquid can become supercooled, ready to freeze at the slightest disturbance. Once ice begins to form, It grows rapidly by drawing water vapor away from surrounding droplets, increasing the cloud's ice content. As a result, much of the cloud becomes composed of crystals rather than liquid. Depending on temperature, these crystals may take the form of plates, needles, columns, or branching shapes. Unlike liquid droplets, they interact with sunlight in complex ways, producing halos, arcs, and other optical effects. Ice also alters how precipitation develops. Crystals gather moisture, grow heavier, and eventually fall as snow or sleet. Even when the ground remains above freezing, the cloud itself may still be dominated by ice. Winter clouds therefore operate with a different internal chemistry than summer clouds, leading to distinct visual displays and weather behavior. Cold air can significantly intensify certain smells. As temperatures drop, the atmosphere becomes denser and less turbulent, slowing the dispersion of airborne molecules. At the same time, cold conditions allow scent molecules to concentrate closer to the ground, making the human sense of smell more sensitive. Odors that would quickly fade in warm air become more noticeable and linger longer. This effect is often apparent near forests, industrial areas, or residential zones, where the scent of wood smoke, soil, or vegetation becomes sharper. Chemical reactions also proceed more slowly in cold conditions, allowing some compounds to remain intact and travel farther before breaking down. Frost or fog can temporarily trap these smells, releasing them again when sunlight warms the surface. Together, these processes create a seasonal pattern in which the same environment carries a different scent profile depending on temperature. Winter does not merely quiet the world, it reshapes the movement and chemistry of airborne molecules, amplifying certain sensory signals. Frozen lakes can develop rings and circular patterns that scientists are still working to fully explain. During winter, some lakes display mysterious circular features on ice or water surfaces that appear without obvious warning. These rings can span large areas and often have sharply defined edges. Several processes may be responsible. Heat rising from underwater springs can thin ice in circular shapes. Rotating currents beneath the frozen surface can trace subtle spirals visible from above. In other cases, methane released from lake sediments creates round melting zones. These features can persist for days or weeks before fading. Because each lake has its own currents, sediment structure, and thermal behavior, the size and form of the rings vary widely. Researchers track them using drones and satellite imagery to uncover the mechanisms behind them. To those who encounter them from shore or air, the circles can appear almost intentional, as if drawn by an unseen hand beneath the ice. Winter storms are capable of transporting heat across entire continents. Large-scale weather systems that form during the cold season can tap into warm ocean currents, redistribute that energy, and carry it vast distances. Storms may draw heat from warm surface waters and inject it into cold air masses, releasing it through condensation as clouds develop. These interactions reshape both the structure of the storm and temperature patterns far downstream. Such processes contribute to shifts in jet stream paths, influencing how warm or cold different regions become. Winter storms therefore play a role in balancing global heat distribution. Acting as energy conveyors, they remove warmth from some areas while delivering cold to others. This movement affects ocean temperatures, atmospheric moisture, and even long-term climate trends. Each storm becomes part of a planetary scale exchange linking land, sea, and sky. Snow falling into the ocean behaves very differently from snow landing on land. When snow reaches open water, it encounters a moving, heat-absorbing surface. Much of it melts quickly, forming a thin layer of fresh water that floats atop denser salt water. This layer can alter surface temperature and salinity, influencing wave behavior and the rate at which heat escapes the ocean. When conditions are cold enough for sea ice to form, snowfall becomes part of a more complex system. Snow accumulating on thin ice can weigh it down, allowing seawater to flood the surface. When this mixture freezes, it produces a distinct type of sea ice, unlike ice formed directly from ocean water. Snow also insulates sea ice, slowing its thickening while protecting it from melting during sunny winter days. These interactions shape the strength, thickness, and movement of polar ice. The meeting of snow and saltwater produces outcomes unseen on land, influencing both weather patterns and marine ecosystems. Winter can even create natural lenses made entirely of ice. When water freezes into clear, bubble-free forms, it can bend light in precise ways, shaping brightness and focus across frozen surfaces. In these moments, ice becomes not just a solid state of water, but an optical medium, subtly redirecting sunlight through the cold landscape. Droplets that freeze into rounded beads on branches or stones can act as tiny lenses, subtly enlarging the textures beneath them. On larger frozen lakes, gently curved ice surfaces bend and concentrate sunlight, creating bright patches that drift across the ice as the sun moves through the sky. Even slight variations in the thickness of clear ice can distort vision, stretching or compressing objects seen through it. Under the right conditions, rapid refreezing after partial melting can produce smooth ice domes that function like magnifying glasses. These natural lenses reveal fine details of ground or water below, offering views impossible at any other time of year. People walking across transparent lake ice may notice rocks or plants below, appearing warped into unexpected shapes as light bends through frozen layers. In this way, winter becomes a season of unintentional optical experiments, shaped by the interaction of sunlight and frozen water. Frozen ground can trap gases that are released again when thaw arrives. Throughout winter, soil freezes from the surface downward, locking moisture and gases in place. Microbial activity slows dramatically, allowing organic material to remain largely intact. As freezing deepens, carbon dioxide, methane, and other gases that would normally escape become sealed within ice-filled pores. When spring warmth finally returns, thawing soil releases these gases rapidly. This effect is especially pronounced in wetlands and tundra regions where large amounts of organic matter accumulate year-round. As the soil softens, microbes reawaken and resume decomposition, accelerating gas release even further. Good night.